Hello, everybody. Julianne, Sarah, and I are the Tooth Savers, and our project was to develop a real-time force-sensing laryngoscope blade for use in intubation training. Intubation is the process of inserting an endotracheal tube into a person's airway for ventilation into the lungs via a laryngoscope, which is an instrument used to lift up soft tissue. The problem that our client, Dr. Woods, is facing is that during the intubation training sessions that he holds, there's no way to objectively tell how much force is being applied from the blade to the mannequin teeth. So as his trainees enter the clinic, they are causing dental trauma on patients. And this can be extremely detrimental. Malpractice claims are the biggest form of claims against hospitals at about 29% because of dental trauma. And also, speech problems can affect children for the rest of their lives because of dental trauma. So because of this, there was a need to develop a real-time force sensing laryngoscope blade that could alert the user about when they're applying too much force. With all this said, we came up with a few requirements that were necessary. First, we wanted to have minimal additional weight and thickness. Also, our device needed to be able to be powered for more than 4 hours. The extraction time needed to be also very minimal, and the device needed to have almost no obstruction at all.
And we went through several design iterations on different components of the laryngoscope. So looking at our voltage amplifier, we actually started with an op amp, and then we moved to a load cell amplifier. For our sensor, we had a thin sticky sensor, and then we moved to a thin beam strain gauge, and we finally ended up with our load cell pressure sensor. For our power supply, we started with batteries, and then we moved to a battery pack.
3 design analyses got us to our final prototype, the first of which was understanding the critical force which breaks teeth. To obtain this value, we put together force calculations with normal and shear stress calculations to achieve a result of 606 newtons. Next, we wanted to understand where the upper incisors make the greatest interaction with the laryngoscope blade. This is where we placed our loading plate. Next, we needed to justify the length of the loading plate. We did this by understanding the reaction forces and determining that they did not vary over 13%, which ensures a high factor of safety.
So the considerations Sarah just mentioned led us to our final prototype. It's a modified laryngoscope that allows us to alert the user about when they have reached that critical force. And we wanted to highlight a few key features. The first is our loading plate, which meets our requirement of being thin while allowing us to get all the force values from the mannequin teeth that we need. Also, we have a robust loading cell that allows us to get accurate data on that loading force. Also, if you look to the right, we have a picture of our loading amplifier, our alarm, our microcontroller, and all these things allow us to be able to alert the user in real time about that force value. And if you look at the bottom, we have 2 pictures of our final prototype.
All of the components that Ryan just talked about inside of the laryngoscope handle can be seen in figure 8. It has a sensor with Wheatstone bridge that's connected to a voltage amplifier, which is connected to a microcontroller, which also controls the light and alarm. Next, I'm going to talk about the software breakdown. Our breakdown incorporates an Arduino, a USB connection, and computer. C++ is able to alarm the user of when there are values that are over the critical force. And then the C++ code can also read and write data from the EEPROM. When connecting the computer, it can also read and write from EEPROM using a Python script, which also allows the user to visualize data by creating a CSV file.
So there were a couple of verification tests that we had run, and they all passed. Some of the validation tests that we want to look at are obstruction, the intubation procedure, lighting, and then the inaccuracies of force. The next steps that we want to do are to do further validation tests and also create a user interface that will plot automatically. And then we want to embed a power source, and our client would like to actually do a study for dental trauma. So with our device, this should be able to significantly curb the amount of dental traumas there are in the amount of cases. Thank you so much for watching.